Hello everyone, hope you are doing good. Welcome to today's daily Leetcode challenge. Today we have a medium question and it's day 22. As you can see, I have again reached 50 questions target and our aim here will be to go further, right? So yeah, coming to today's question. Today we have a medium level question and it tells about how to find the minimum score of a path between two cities. So the question here is very simple and clear. For example, you are given a positive integer n representing n cities. See, one thing is very clear. Here they are not using 0, they're using 1 to 1, right? You're also given a 2 array road. So, see, this is how it is. 1 to 9 means there is a path with 1 and 2 node, which is shown in this diagram, and which has a weightage of 9, right? This is how it is. So, if you take 2, 4, and 5, it means there is a path between 2 and 4, which has a weightage of 5, right? This is a path. Similarly, the other ones you can interpret in the same way. It means there are four nodes named for 1 to 4. Okay, there is no zero involved here, so keep that in mind. So yeah, these are the constraints. The road length will be of range 10 power 5. So we need to make a solution which is of O of n plus e. N is the number of nodes and e is the number of edges, right? That is the best possible solution. And if you are aware of how the traversals are, so you must be knowing that BFS and DFS are the best traversals, which will be giving us this kind of complexity. But see, there is a trick. Normally, in the questions, they will ask the shortest path and all that stuff. But here, they are not asking such a thing. They're asking the minimum, that is the smallest edge in the path between node 1 to n. That means here, as you can see, the node 1 is here and the node n is 4. The node 4 is here, right? There are many paths from 1 to 4, but we will have to find the path which has the smallest edge. Okay, so what that means is, see, I can go from 1 to 4 through the 7 also, right? So the 1 is 7. Then I can go to 4 from 1, 2, and then 4, right? So the minimum in this case will be 5. That's why the answer is 5. Now see the below example, it will be very clear for you now. The node 1 is here, the node n, which is 4, is here, right? I can go with via 3, okay, 1, 3, and 4. So the minimum h in this path will be 4, right? But if I go first, say I'm going from node 1 to node 2, back to node 1, then 3, and then 4. In that case, if I see, the smallest edge will be 2 in the whole path. Okay. First, I'm going from node 1 to node 2, node 2 to back to node 1, node 1 to node 3, and node 3 to node 4, right? In this case, the smallest edge will be 2. So, answer is 2. So, I think we have understood this correctly. We need to return the minimum distance of a road in this path. Okay, here we are not asking the shortest path. Here we are asking the shortest road in this path. Okay, the edges are the roads here. We just need to know the shortest road in this path. You can take any path for that reason. Okay, but it should have the shortest edge. So what is the logic here? Is, see, one thing they have given a clue here. See, this question you cannot solve just like that, because see, it will go for infinite loops, right? If you are aware of how these problems are being solved, how the DFS, how we are maintaining a queue, you must be knowing that we can't keep on like simply searching for the shortest path, right? Because see, they have already mentioned that. Yeah, we can take road multiple times. They are mentioning, and this is the biggest thing. See, there is at least one path between node one and n. And see, they've also mentioned that the cities is not necessarily connected. That means each node may not be in the same connected component. See, one thing is very, very clear now. See, this without this, we cannot solve this question. Okay, I will tell you why. See, they are clearly mentioning there is at least one path between node 1 and node n, right? Which clearly indicates that node 1 and node n are in the same connected component. Let there be any number of connected components. We are not bothered about other edges or other nodes. We are bothered only about node 1 and node n, right? And it's very clear from this statement that they will be in the same connected component, right? If they are in the same connected component. But see, the next challenge is how do we frame the solution here? It will go for infinite loops if we keep revolving like that, right? Normally, we'll keep a visited asset, then we will not be visiting the nodes again. But in this case, see, if we take this solution, I'm going from node 1 to node 2 and back to node 1, then 3 and then 4, right? So there is no logic here, like why should we do like that and how we can do like that. If we are allow, see, if there is a loop here, then it will be going on revolving, right? How to avoid all these things? The best possible way to do that is, see, I know that My answer is the shortest edge between any possible path between node 1 to node n, right? What I will do is I will start from node 1 and I will try to see what are the nodes in my connected component. Okay. So one and n will be in the same connected component. I will try to find the other nodes as well in the same connected component. Then I will find the shortest edge in my connected component. I will not be traversing simply like that. I will just find which is the smallest edge. That's it. So how that is being done is I will show you here. First, I am using a dictionary to store the edges and their weights, right? This how it is being. If I is not an edges, declare I and store it C. For each I, what I am storing, J is the component. For example, see 1 and 2 if I take, for 1, 4 and 2 will be saved, right? Because it's connected to 1. And with 4 and 2, I will save 7 and 9 as well, which is their weight. So I will quickly show you how it is being populated. Yeah, as you can see, with 1, there are two things being stored here, right? First is the second node. First is the second node. Then is the fourth node, right? One is connected to 4 and 2 in the first table, as you can clearly see. And the weights are 9 and 7, right? 9 and 7. The same is the reverse case also. Now see, 1 is connected to 2, so 2 is also connected to 1. That's what we are doing here. Now see, here we are taking I and we are storing the J. In this case, we are storing the J, sorry, we are taking J and storing the I, right? We are doing the reverse. For example, for 1 I will be storing 4 and 2, and similarly for 4 I will be storing 1 and 2. That's the basic idea of it. Now see, the character component having 1 will also have an as per the question, right? This point is very clear, right? Character component having 1 will also have an as per the question. Now finding all the nodes in this component. We'll find all the nodes and all the edges in this component. And while traversing, we will also keep a count of the shortest edge, right? And we see this is a BFS solution. This is going to be BFS solution. In all my solutions, you would have seen that I prefer BFS only. I don't prefer depth first search in such solutions. Okay, so if you are aware of what BFS is, you must be knowing that there will be a queue involved here. Then there will be a visitor set involved here, right? Apart from these two, this is what we are going to maintain to track the shortest edge while we are traversing through the nodes in this connected component, right? See, normally you would have seen if we are to traverse all the connected components, we will run a for loop so that all the nodes we start with at least all the nodes at once at a time, right? See, we'll write a for loop so that for each node we are starting, right, and entering into its connected component. But in this case, it is not needed. I am very much sure. See, what I am starting with, my queue is starting with node one, right? I'm very much sure that my node n will come in the same component, same connected component as node one. Node n will come in the same component as node 1. That's why I am not bothered about other connected components. Let that be. Okay. We we are going to get our answer only from this connected component. Okay. So while this queue is not empty, this will be run. This is a set, right? Set means it's like a hash map. Okay, it's like hashing and storing the keys. Okay. So what I'm doing is I will pop the leftmost element in the queue. I will store it in the node variable. Node is the number. Okay. For example, it will be 4 and 2 and 3 like that. It's the number of node. The nodes number. Okay. For example, in this case, node 1, node 2 like that. Okay. Then I will add it to my visited node. So what is visited is doing, it will add all the nodes which we have already visited so that we don't visit it again. Otherwise, it will be an infinite loop problem, which I have already mentioned, right? See, while traversing, we have to avoid circles and all these things, okay? Otherwise, it will be like infinite loop. In my visited array, I am showing the node which I have visited, okay, which is popped from my queue. Now, for m comma n in edges of node. See what is stored in edges of node. J and K are stored. What is J and K? J is its adjacent node, K is its weight. For example, if I talk about the node 1 here, I will be storing 2 comma 9 and 4 comma 7. 2 comma 9 is the node which is connected to 1 is 2 and the edge between them is 9. Similarly, 4 comma 7 is the node connecting 1 and 4 is has a weight 7. Okay, so M is the node and is the weight, right? If M is not in the visited, only if it is not in the visited, I will be inserting it inside the queue, right? And I will be also doing answer is equal to minimum of existing answer at the end, right? This is that answer. See, this is the main trick. So this only we are going to get the solution, right? I will also show you how it is being populated, and finally we are returning the answer. Okay. This part makes the solution most easiest part. See, my aim is I'm doing a simple DFS to find all the nodes in my connected component, which is connecting node 1 and node n. It is so some components should be there, right? And for each of those components, as I'm traversing, I'm also noting the shortest path. Okay. See, and it's just a edge. It's just a edge. It's not the shortest path. Just the shortest edge. Okay. So answer variable is storing the shortest edge here, right? In this case, the shortest edge is the answer. So I will quickly show you how the whistled array is being populated. We will see the example also. So in this case, as you can see, this is my connector component, right? So as I traverse from 1 to node 4, I can clearly see that other components, other nodes in this are 1, 2, and 3, right? So this is how it is being populated. We started 1, and we are also getting 2 and 3, and finally M4, right? Coming to the second example, you can clearly see this also is the same way. For going to 1 to 4, there are other nodes involved in this connector component are 2 and 3, right? This is what is happening here, okay? And finally, we're returning the answer. Coming to time and space complexity, see, time complexity will be O of n plus 3 because see, we are doing a simple BFS only, okay? We are only traversing through the nodes and edges, maybe more than one number of times. See, if one is for the making adjacency list, this is how, see, you could call it as adjacency list, right? It's like, its work is like that of adjacency list only. It is, may not be in the form of a matrix, but still it's acting like adjacency list, okay? And this is how we are traversing. So you can clearly understand that the time complexity is O of n plus c, where n is the number of nodes in this graph and e is the number of edges. Okay. And coming to space complexity, see, I am not using any array as such. See, these are the arrays but used, but we are also like making it empty before we are ending the loop, and we are using set array. Set will show the number of nodes, so you can see the time complexity will be O of n, where is the number of nodes. So yeah, I hope I have explained the solution. I will again repeat, see, in this, we are not trying to find the shortest path. We are just trying to find the shortest edge in the connected component, which is connecting node 1 and node n. This is all we have to do. See, if they had not given this, this problem is not solvable. Okay. If node 1 and node n are not in the same connected component, there is no way to tell that. There is no way to find out how the shortest path will be. This only because of this question is solvable. Okay. So please keep that in mind. And yeah, friends, that's all for today. If you really like my content, please like and subscribe. This motivates me a lot. Thank you once again.